sostener este seminario, que es de suma importancia para los aspectos geológicos y ecológicos. Agradecer a Silvina, a Leandro, al CEIDE, a la Fundación Williams, que permitió, digamos, que yo pueda estar entre nosotros, y por supuesto la participación de todos ustedes. Creo que el tema, digamos, de descarga de agua subterránea, descarga submarina de agua subterránea, es un tema que cada día va adquiriendo mayor trascendencia. Digamos, un tema que, digamos, es invisible, pero hay elementos y herramientas para poder ir detectándolo, y creo que eso es lo que van a ir trabajando durante el seminario. Destacar que esto tiene una importancia desde un punto de vista de las aguas subterráneas, pero también una importancia desde el punto de vista oceanográfico, ecológico, de distintas disciplinas que van a ayudar a esto. Es decir, hasta hace poco se pensaba que gran parte de los nutrientes que llevaban al mar y quedaban, digamos, que activaban la biología marina, era producto de la descarga de las aguas superficiales. Y en este momento se reconoce que un mayor porcentaje de aguas superficiales es justamente la descarga de aguas subterráneas. Y nosotros tenemos más de 4.000 kilómetros de costas marinas donde el tema es muy importante y prácticamente inexistente el conocimiento. Tenemos también la costa del Río de la Plata, que a diferencia de lo que ocurre en el mar, digamos, lo que está descargando en el agua dulce es el agua salada. Otro tema también que es muy importante. Y esta relación agua dulce y agua salada se da también en médanos de dunas interiores, donde hay explotación de agua subterránea, problemas de contaminación, e inclusive en la explotación del litio. En la explotación del litio también hay una relación agua dulce, agua salada, que va a regir las posibilidades y la extensión que puede tener la explotación del agua salada, ya que existe esta relación agua dulce, agua salada, que es de suma importancia para desarrollar, digamos, todo lo que es cálculos de reserva. Así que bueno, espero que tengan una buena jornada en estos dos o tres días que van a estar y que puedan aprovechar todo el conocimiento que les puede brindar John a partir de su experiencia en distintas costas del mundo. Muchas gracias y bueno, adelante Silvia.
Gracias, Pedro. Bueno, no queda mucho más para decir después de lo que dijo Eduardo. Agradecerles de vuelta a ustedes, a la Fundación y sobre todo a John por estar acá. Les voy a contar un poquito quién es John, pero muy brevemente. En este momento él pertenece a la Universidad de Kiel, de Alemania, pero como puso ahí en la presentación al inicio, él estuvo trabajando también mucho tiempo en la Universidad Sacred Heart de Estados Unidos. Primero Kiel, después ahí, después ahora volvió otra vez a Kiel, y bueno, el trabajo que venimos haciendo en conjunto con las distintos lugares, instituciones que estuvo John y nosotros desde el grupo del SEIDE, bueno, data desde el año 2010, ¿sí? Así que bueno, ya tenemos 15 años de trabajo y colaboración en conjunto, y bueno, ahora la idea es, como dijo Eduardo, gracias al subsidio de la Fundación Williams, de profesor visitante, pudimos traerlo a él y a su aparato de detector de radón, que después ya les va a comentar de qué se trata, para continuar justamente con estos estudios de descarga submarina en la costa atlántica bonaerense, que es bueno, un sector que nosotros tenemos como área fundamental de estudio. Así que bueno, los dejo para que empecemos ya el curso con él. El curso va a constar de 4 días, como ya saben, hoy y mañana, y la semana que viene también, miércoles y jueves, en los mismos horarios, y en un poco ahora les va a contar la dinámica de cómo van a ser las siguientes clases. Gracias.
Gracias, Silvia. Hola. No hablo español. Yo comprendo un poquito español porque hablo italiano. So, we will see. I will obviously speak in English for these 4 classes, but I've been living around the world in my life, and I've taught many Germans, Italians, so I'm used to speaking, let's say, as slowly and clearly as possible. That being said, if I speak too fast, stop me. If you want me to repeat something, no problem. I'm here to talk about an interesting subject, but also in a way that you really learn about this subject. And so please do not hesitate to say, please go back, I would like to hear a little bit more about that. Also, from what I heard, you will be with me, we will be working together for 4 classes, so a total of 8 hours. That's a good amount of time. What that means is that I don't want to be the only one talking for 8 hours. You'll get sick of me at some point. So I will ask you questions too. This will be a bit more interactive, and therefore, hopefully, more exciting for everyone here. Yes, I was introduced a bit, but I just want to add a couple things. My life is a bit complicated. I am from New York and did my PhD on the topic of submarine groundwater discharge, and I'll tell you a story in a few minutes about that. After finishing my PhD, I moved to Venice, Italy, where I continued to do research on this topic. But while I was there, I started shifting to other topics as well, which I will briefly introduce because they're also interesting to hear. After working in Venice, I moved to Kiel in Germany, which is a very large marine science city. So it's mostly coastal and deep water marine sciences that's done there. After 3 years in Kiel, I moved to Connecticut and worked at Sacred Heart University as a professor for 3.5 years. While in Kiel, I had already met Silvina, so this is what, 15 years ago? 15 years ago we knew each other. And we still talk to each other, so that's a good sign. Yeah, so then I was a professor at Sacred Heart University, and while at Sacred Heart University, I was working in a biology department. So I'm a classically trained coastal oceanographer, mostly in geological oceanography. But I moved to a biology department, which meant I had to learn a bit of biology, which was difficult for me. I remember my first year, I was actually teaching molecular biology to the students and reading the book like, oh my God, oh my God, oh my God, the night before. But I got it done, we got there. But the point is, while I was there, I learned a lot more about the ecological aspects of submarine groundwater discharge, as well as trying to understand how to protect coastal zones via nature-based solutions. And so that's something that I will talk about during these 4 days as well. My life took a bit of a left turn at some point, and I moved back to Germany. It's a long story, opened a few restaurants. The restaurants still go, but all that time I was still teaching at Sacred Heart University online, mostly GIS courses. And then recently, in the last couple of years, I've gone back full time, and now I'm a professor again in the University of Kiel. So that's kind of the long story short of why I'm here. And over the next 4 days, we're going to be talking about a few different things. The main topic is submarine groundwater discharge, or groundwater in general, or even water, we'll talk about it. And I love this photo here, because when we think about submarine groundwater discharge, we often think about some spring that's coming up under a coral reef, for example. But the truth is, a lot of submarine groundwater discharge is just this. Now, this is low tide. At high tide, water is coming out of each of these little I don't know how you would call them, creeks, rills, something like that. That's all fresh water that's coming out. And I also like this picture because you can see that the animal life also seems to be attracted to this fresh water, or maybe it's cool water that's coming out. So it's colder than the hot surface water. So there is an interaction with biology, and it's shown just in this photo and just in these little streams, beach streams that are coming out in the intertidal zone. Now, some people might call this intertidal groundwater discharge and not submarine groundwater discharge, but generally when we talk about submarine groundwater discharge, we also talk about this intertidal zone. So I like this one. It shows us a lot. It tells us a lot. So when you think about this, and I will show you some springs, when you think about this, it's not just springs. It's also this very small process that's happening everywhere on the coast. If you go down to the beach here, you'll see it at low tide. You'll see these springs forming. Some of that may just be the high tide that went into the sand and comes back out. But some might actually be fresh water coming off from the freshwater lens underneath the dunes. So today I'm going to introduce this topic. We're going to explore the history of this work and this research and talk about its implications. Tomorrow, I'm going to focus more on the quantification of submarine groundwater discharge. Today I will quantify it, or we will quantify it together via a simple method. Tomorrow we'll get into a bit more complicated method using radioisotopes, so radium and radon. Today and tomorrow is kind of a melded talk. So we'll just see how far we get today, and then we'll just continue tomorrow. Hopefully that will be closed out by tomorrow at 11 o'clock. If not, we'll continue next week, but it should be. And then we can move on to understanding some nature-based solutions and the role that groundwater plays in nature-based solutions to coastal protection in the face of climate change. And then we're going to end by talking a bit about water management, specifically in small island developing nations. Because as we all know, water is one of the most critical resources out there, if not the most critical. Some might say air, water. But water is obviously a very limited resource, and particularly in small island developing nations. And what you'll hear about, what you probably already know, is that small island developing nations are the most vulnerable nations to climate change. Small island developing nations only produce less than 1% of the world's greenhouse gases, but they are the most vulnerable to all of the things that we're doing out there, and particularly the water management is a big issue. And that also is, now we're looking at groundwater, but probably less in the discharge direction, although we'll talk about that a little bit, but more in the saltwater intrusion direction, which is something that Silvina has been focusing on for many years as well. So those are kind of the four talks, or four parts of this seminar that we're going to go into. But we're not going to only have me talk, right? We're going to interview. Okay, good. So before I really begin, I just want to tell you the story of why I started working on submarine groundwater discharge, because as a 22-year-old, it's not the first thing that comes into your mind when you want to go into marine or coastal research. Most people that are working in marine sciences, I was not a geologist, I was a marine scientist, are more interested in studying dolphins or biology. And I particularly was interested in working with beaches. I was always interested in trying to understand beach morphology, beach processes, erosion, things like that. And I walked into my professor's office and I said, I want to work with you, and I'm very interested in doing your work on beach profiles, on beach morphology, understanding changes in beaches over time. And he looked at me and he said, how about submarine groundwater discharge? I'll send you to Venice, Italy this summer. And I said, I get to go to Venice and work on submarines? Sure, I'll do that. Of course, it had nothing to do with submarines. It had to do with the groundwater discharge. And it all starts with this image. This is the first scientific image of submarine groundwater discharge. Here we see a submarine spring. It tries to show why a boat, when it goes over these submarine springs, notices a change in the water surface, and honestly, a change in the density of the water, which could cause some problems. And this figure is from 1856. So we've known about, scientifically, about submarine groundwater discharge for over 170 years. And looking at this figure, you really start to see that they kind of understood what they were talking about, right? So here, it's tough to see maybe the contrast here, but here we have an aquifer. This is a different substrate as up here and down below. So this is an aquifer with a relatively high hydraulic conductivity, and it's confined. It's confined. I know that there are some different backgrounds here. So if I'm saying things, terminology that you don't understand, please stop me and ask. But we have a confined aquifer, which means that the aquifer is not in direct connection with the seafloor everywhere. There's some sort of impermeable layer that is not allowing the water to go directly to the sea. It's flowing through this conduit here. It's flowing through this conduit and it comes out like a spring here and just goes straight up into the water. So in the area that's marked as sea, we have a relatively impermeable layer. In the area also marked as C, also relatively impermeable. And the area that's marked as D, a very permeable conduit, which allows for a submarine spring. Have any of you ever seen a submarine spring? They're not probably here along this coast, this type of submarine spring. What you need is you need to have essentially a hard rock geology that has some sort of conduit layers, so like a fractured rock aquifer or a volcano. So you have these volcanic tubes, lava tubes that allow for these springs to occur. And when you do, and you go to the coast, you'll see things like this. So underneath here is a spring, and that's fresh water that's coming to the surface, which has a different density than the salt water. And so it ends up being like oil on water, right? If you put oil on a water surface, the oil will float and it will have a different shimmering layer than the water around it. And this is the case too. This is like oil on water. It's just a spring of fresh water that comes up. And so if you go to places that have volcanic activity, if you go to places that have fractured rock aquifers, or potentially even limestone aquifers, you will see springs in your coastal zone.
Sean, what size is it?
What size is this spring? This is about 3 meters by 3 meters. So it's a large amount of water. And this is what we would call point discharge. Point submarine groundwater discharge. Looking at a similar spring underwater, you can see here how it shimmers differently. Because of the density differences, you can see this spring. When it comes to point discharge, it's such a large volume in a small area that you can see it. You can see it, you can feel it. You can go over it and you'll notice that it's colder usually than the surface water around it. Or in some cases it can be hotter, it depends on where it is. But often these are in areas with warm waters and the cold groundwater is coming out. This is in Florida. Florida has a lot of limestone. It's a karst geology. And so there are many springs in Florida. And often where the spring is, the benthic area or the bathymetry goes down. So the sand has been blown out over time where the spring is. Most of the places where we work, we don't have these easy to spot springs. We'll get to that a little bit later. But where it is like this, it's much easier to do this work. As I was starting my research, and that's why this photo looks bad, this is already 20 years old, I had the opportunity to work in Mauritius, in the Indian Ocean. Mauritius is a volcanic island, and so there are lava tubes. And there are many springs in the area, and in fact, they often block the springs off because they're afraid when people swim over the springs, there's such a strong change in density that people can get disoriented and maybe even drown. So they feel like there's a difference in what's happening. So they block them off. And this was a large spring underneath here. And we tried to cap the spring. We tried to put a very large, let's say, garbage bag over the spring and put a hole through the top to see if we could measure how much water was flowing through that hole. I don't think I've ever told you that. It didn't work. It didn't work. We were able to measure other things there, use other types of techniques to measure how much was flowing out, but that didn't work. It was too much. The water, we couldn't get it down. So when we talk about a submarine spring, we talk about once again, a confining layer on at least the upper part of the area that then pushes that fresh water below, and then it comes out as a spring in the coastal zone. And so this is a classical image of submarine groundwater discharge here. I'm sorry, this is a bit small to see, but it says submarine groundwater discharge equals meteoric water, which is groundwater of recent atmospheric origin. What's that second word there? So, actually I don't know what that says, but water incorporated into rock pores where the rock forms, and recirculated water. So here we have our typical profile of land to sea. And then we have our sea surface, and so we know that this is the ocean, this is the sea floor, and what we have is a water table that when it rains, the water table will rise. If it's been dry for a long time, the water table will fall. But that water table tends, in most cases, to be above sea level. It tends to be above sea level. If it goes below sea level, because we're pumping out too much water, then the water will rise. But if it's above sea level, theoretically we get a small amount of submarine groundwater discharge at this interface. So it just flows out at this interface. And that's similar to that first picture that I showed you with ducks in the water. Then we have, in this kind of classical diagram, below our freshwater layer, we tend to get a bit of salty water that comes in. So even if our water table is above the sea surface, there's usually a bit of salt water that's going in below this freshwater lens. And that salt water tends to come in and go back out. And that's called recirculated submarine groundwater discharge. And we're going to talk about this a bit today and tomorrow because there's a big difference between fresh submarine groundwater discharge and recirculated submarine groundwater discharge in terms of its impact on ecology. Then we have our confining unit, and below we have kind of our confined aquifer and our submarine spring, and somewhere then further into the seafloor there's this mixing once again of recirculated seawater. So how did this all start? Well, the original reason for studying submarine groundwater discharge actually came from the idea of being able to capture that water. There are plenty of places in this world that don't have enough fresh water. And you would go to these places. A good example of this is Bahrain in the Middle East. And the people would see, okay, we have almost no water on land, but all of this water is coming out of these springs. What if we can capture that water and drink it? Get our fresh water from it. And I don't have any images of this, but in Bahrain, they used to send divers down with jugs to the spring and try to get the water directly at the source so people could drink. It probably wasn't 100% fresh. It was already mixing a little bit. But this was the goal. This is how this research started. It wasn't because of ecological processes. It was simply the idea of capturing fresh water. And this continues. So this is an image from about 10 years ago of a group that's really trying to find ways to have tubes that go directly into springs to capture the fresh water that they can drink. So that was how we started to think about this. Okay, submarine springs, you saw the images. They're very clear. We can understand them. We know that there's groundwater coming out, and we want to learn about it.
John, did anybody succeed?
Sorry?
Did anybody succeed in the trial of capture?
It's still a technological issue, right? And so in small cases, they are drinking the water. They are doing this. I mean, I don't know if this is a commercially viable project yet, but this is a lot of water in certain places. And often it's in places that don't have surface water freely available. So, Silvina was walking in the Dolomites, I guess back in July. Dolomites are a limestone mountain range. And she said to me the other day, it's amazing how little surface water there is there. When you have limestone, when it rains, it basically goes right into the ground. So if often you have springs where surface water is not easily reachable or available. So that's why this connection happened. Of course, over time, we realized, okay, there's a lot of fresh water coming out, but it's probably not just a source of fresh water, it's probably also bringing in other things to the coastal zone. Nutrients, metals, carbon dioxide, etc. So we wanted to learn more about it. We wanted to learn not just about springs, but also about this entire process of submarine groundwater discharge, including the diffuse discharge at the coastal zone. And this diffuse discharge at the coastal zone is basically dependent on Darcy's law. Who here are hydrogeologists or studying hydrogeology? Okay, a few of you. So Darcy's law is more or less the foundation of hydrogeology, right? Who wants to tell me what it says? What is Q?
Rate.
The rate, the discharge of water, the discharge of water. Good. What is K?
Permeability.
Permeability, almost. It's hydraulic conductivity, which is dependent upon permeability. It's dependent upon permeability and porosity.
Yes.
right? So you could have fairly permeable sediments, but if they have low porosity, then K is a bit lower. But it's both permeability and porosity that determines your hydraulic conductivity. What's DH over DL?
Thickness and the length.
Yeah, the height and the length,
Thickness and length.
which is known as the hydraulic gradient. The hydraulic gradient. So basically, if this is your water table, and this is sea level, then your H is the difference between the water table and sea level, and the length is how far that is. And the higher the hydraulic gradient, the more discharge you have. And what's A, any idea?
Area.
Cross-sectional area. So it's essentially the window that the water is moving through. So when we look at simple to think about, difficult to measure, submarine groundwater discharge that's just happening in this diffuse coastal zone, it's based on Darcy's law. It's based on Darcy's law. So if you have very permeable and high porosity sediments or soils, and you have a strong hydraulic gradient or a large hydraulic gradient, then you should get a lot of discharge. You should get a lot of discharge. So what kind of areas would have a high hydraulic conductivity? What kind of soils would have high hydraulic conductivity?
Sandstone.
Sandy soils. Sandy soils. So what kind of coastline do you have here in Buenos Aires? Sandy coastline. A sandy coastline. So you should theoretically have a relatively high hydraulic conductivity. So one of the things that's driving our submarine groundwater discharge then is this hydraulic conductivity, and the other thing is the gradient. So if you have a dune system, and you have a lot of rain and your water table goes up, then theoretically your discharge should increase. Simple, right? You all understand that? That's good. So theoretically our discharge should increase. When would discharge be higher? At high tide or low tide? Low tide. So this is another important point, that our submarine groundwater discharge is dependent upon tidal levels in this diffuse system, in this non-spring system. So when we have low tide, the hydraulic gradient goes up. Right? Because the difference between the water table is not changing as fast as the tide changes. So the difference between the water table and the sea level is much greater at low tide than high tide. And so if you have areas with a decent tidal range, 1 meter plus, you can really see this in a classical system. Okay, so this brings us to the final one of these images. This is a nice image, very recent, from Adina Payton in 2024. So just last year, where she really tries to show the complete picture of this submarine groundwater discharge process, as well as bringing in some of the chemistry, the biogeochemistry associated with it. So once again, we have our water table, which fluctuates over time. When it recharges, this is kind of our stable water table, and up here we have fresh coastal groundwater. And when we have fresh coastal groundwater, we can get fresh discharge right at the coastline. Down below, we have this saline recirculation, so the salt water that comes in, the salt water that comes out. And then in between, we have an area that's known as the subterranean estuary. Does everybody know what the term estuary is? Forget it. Sorry?
What's that?
Sorry?
History.
Estuary.
History.
So the estuary is
Mixing.
a mixing between salt and fresh water. And just like if you have a surface water estuary, a lot of chemical processes occur in the subterranean estuary. When salt and fresh mix, a lot of processes happen. You get desorption and absorption of different chemicals to sediments. So certain chemicals desorb from the sediments when they get moved from fresh to salt water. It means they're released from the sediments. They go into a soluble liquid form, and then they can be available to the ecosystem to be taken up into phytoplankton, organisms, etc. Other chemicals zorb when they reach a higher salinity. So actually, because of the ionic bonding, they actually are taken into the sediment. So processes, lots of processes occur in an estuary. Lots of biogeochemical processes occur in an estuary. So this mixing zone between salty groundwater and fresh groundwater is an interesting place. It's an interesting place. And it's particularly interesting for radium. Tomorrow, well, even starting today, we're going to talk about radium. Radium is a naturally occurring radioisotope. It's a daughter of uranium and thorium. And radium has an interaction with salinity. So radium that's attached to sediments, when it gets to a salinity of 7 or 8 parts per thousand, it will release. It will release into the water column. And so radium measures what's happening in this subterranean estuary. But it's really important to remember that because we're going to go back to radium. Where radon doesn't. Radon is just another thing we're going to talk about a lot in the next 2 days. Radon is not affected by salinity because radon's a gas. So radon just releases from the sediments directly into the water column as a gas. Has nothing to do with the water, and therefore it has nothing to do with the salinity. Radium does. Remember that. Radium has to do with salinity, radon doesn't. Okay, good. So we start thinking about this process of SGD not just in the sense of springs. Now we're thinking about it also in this diffuse SGD that could be happening everywhere. And as I mentioned, radium is an important radioisotope, which we use to look at SGD. And there was a professor in South Carolina named Billy Moore, who's like the godfather of this research, who went around the world, literally, basically took cruises all over the oceans of the world, measuring radium. And he wrote a seminal paper about 10 years ago, in which he says that, or they say, but it was really Billy Moore's idea, that between the Atlantic and Indo-Pacific Oceans, radium suggests that SGD is 3 to 4 times greater than the freshwater flux into oceans by all rivers combined. 3 to 4 times more fresh water is coming into the oceans via groundwater than all rivers combined. You guys are a couple kilometers away from a very big river here. Do you believe that? We'll get into that. It's hard to believe. It's hard to believe that there's more water coming, more fresh water coming into the coast, into the oceans via groundwater than rivers, globally. Globally. There are some really big rivers in South America. Really hard to believe that. But he wrote this paper and it was like mind-blowing. Now, oh my gosh, we have a lot of groundwater coming out there. So we have to start thinking about this. And I think the first thing that we have to start thinking about is, why is it important? We'll get into this a bit later, why it's important. It's important because of its chemical contributions. It's important because of just simply the amount of fresh water that's going into the ocean. But the question is, what is really important? And this is something that I'd like to really talk about a lot in the next 2 days, is how much of it is fresh water and how much of it is recirculated seawater. So to me, although recirculated seawater is important because of the estuarine processes of release, when we really think about SGD's importance in ecosystems, continental freshwater, how many new nutrients, how many new chemicals are getting into the coastal zone is really, to me, something that we need to nail down. So keep in mind, Billy Moore's paper was done with radium. Okay, we'll get to it. Okay, so where are we? Just take a look at my time. I tend to talk a lot. Okay. So we are now really understanding that SGD is important, and SGD is in a lot of different places. It's not just submarine springs. It's not just diffuse discharge. It's not actually that easy to determine what exactly SGD is. And we start to think about it in many different ways. So we think about it on a size scale, so how big SGD can be, and on a temporal scale, how long it takes. So for example, pore water exchange. So just every time a little wave goes over the sand, it's pushing water through the sand. That's pore water exchange. That's happening on the order of seconds. And it's happening on the order of centimeters. So that's something that it's an important process, but is that SGD? Depends on who you ask. If you ask Billy Moore, maybe he would say yes. If you ask another scientist, maybe they would say no. So we start thinking about these things. We also think about tidal pumping. So is tidal pumping this longer period movement of water in and out that's then kind of, the tide goes up on the beach, goes into the water, comes back out, goes into the sand, comes back out. Is that SGD? Is that SGD? So we're trying to now understand, what we're talking about when we get to SGD. And we will try to nail this down a bit better in the next few hours. Then the question is, how do we actually measure it? How do we measure it? Do we measure it using direct measurements of SGD? Do we measure it using remote sensing measurements of SGD? Do we measure it using tracers, artificial or natural radioactive tracers of SGD? And these things, these two graphs, we're going to now get into and discuss what they are. Okay. And to do that, we're going to get into history of SGD measurements. So this is my first day ever measuring SGD when I still thought I was going on a submarine in Venice. And no, it wasn't a submarine. I was prepared to get in the water. This is a picture 24 years ago, from an area in New York where we were doing an intercomparison experiment of SGD using different methodologies. And we're going to get into those methodologies now. Okay, so the first way we measure SGD is via a seepage meter. A seepage meter. This is a point measurement of SGD. a point measurement of SGD, and it's a really simple idea. Basically, you cut off the top of an oil drum. You clean it. Please clean it. You cut off the top of an oil drum, and you go out into your beach, into your coastal area, and you push this oil drum into the sediment, 10 centimeters into the sediment, and you put a little nozzle on it. Little nozzle. And then you attach a plastic bag, deflated plastic bag, to this oil drum. And the idea is that theoretically any water that's coming up through the sediment is displacing the water that's left in this drum into this bag, and you can then collect it and measure it. You can collect it and measure it. So your oil drum looks like this, or if you don't have as much money, maybe you get some old rusty ones like this. Don't do that. Prefer using stainless steel ones. They're a little bit better. And then you put them into the sediment. And in a perfect world, you have 12 of these things. And you can put them into shore perpendicular transects. And maybe 4, 4, and 4. So you get a bit of a spatial coverage. And you put them in the ground every 10 meters or so offshore. And then you put the bag on it and you let it sit for 30 minutes or so. And then you can collect it and measure it. So I have a question for you. If our seepage meter has a radius of 29 centimeters, and you leave it on, the time that you leave the bag on is 30 minutes. And you collect 1 liter of water in those 30 minutes. What is your discharge in centimeters per day? Because this is how we determine, this is how we describe how much groundwater is going out, in centimeters per day. That means centimeters of groundwater per square centimeter of sediment surface per day. So, you put your steel drum in there, and your steel drum has a diameter of 58 centimeters generally. So the radius is 29 centimeters. You put it in, you let it measure for 30 minutes, and you get your bag out and you measure it, and it's 1 liter of water. What is your discharge in centimeters per day? How would you go about that? So first question is, 1 liter, sorry?
First, look at the cross section.
Yeah, so you got this area, right? So what is the area here? It's a bit difficult. And you want it in centimeters, because everything's centimeters. Does anybody have a calculator on the phone?
People remember, people remember.
Sorry?
By
By radius.
Yeah, but we're going to actually do it, so what's the answer?
26 square meters.
No, not 26 square meters. 2,600 about
Sorry.
cm cubed, right?
Yes.
Sorry, cm squared. Cm squared. Okay, good. How many cubic centimeters are in a liter? 1,000. So, 1,000 cubic centimeters divided by 2,600 square centimeters is your first step. Sorry, I'm trying to work on this side because of the camera. So I might have to do this twice.
In 30 minutes.
In 30 minutes,
How many per day?
so exactly times 30 minutes, over 30 minutes, times how many minutes are in a day? 1,440 minutes are in a day, I believe. Yeah. Sorry, that's minutes per day. So, it's 1,000 centimeters cubed times 1,440 minutes per day over 2,600 centimeters squared times 30 minutes, because we measured it for 30 minutes. So our centimeters cubed cross out, so we're left with centimeters at the top. Our minutes and our minutes cross out, so we're left with days on the bottom, so centimeters per day. And I believe the answer is something like 18 centimeters per day. So that's 18 cubic centimeters of water per square centimeter of surface per day. So that's 18 milliliters of water that are passing every square centimeter of your coast per day. And then you have to multiply that out by how many square centimeters are in a square meter times how many square meters are in your coast, et cetera, and you can get a flux of water. You can get a flux of water over your coast. So 18 centimeters per day is actually a fairly high amount if you had that. We could spend a lot of time calculating how much that would be if we had that for a 1 kilometer coastline, but I think you get the picture. Right? We don't have all day. Okay, so we make these point measurements, and it's simply the discharge equals the volume over the time, over the area. It's integrated over a short period of time. And then you make these measurements. Sorry, this should say centimeters per day on this y-axis. You make these measurements in different places at different times in the tide, and you're able to then understand how much groundwater is coming out in your coastal zone. And we always do this for at least half a tidal cycle, because in a perfect world, you actually get higher values at lower tides. Right? But you see that only happened really in one of these 5 locations, because of what we talked about earlier with the hydraulic gradient. So you always want to do it over a time period. Also, your seepage meter is only measuring 2,600 square centimeters of surface. So you need to have multiple seepage meters out there to try to understand your true discharge.
No, sorry.
Sorry?
This methodology, I mean, for instance, in the beach where we been the other day with the breaking and everything, how do you install that?
So one of the big problems is if you're in an area with breaking waves, it's very difficult to do this, because the energy of the breaking waves is doing 2 things. One, it's going to rip your plastic bag off. If you're lucky enough to get it into the seepage meter, into the water, and not kill yourself as a wave hits you. And the second thing is that the wave actually pumps water through the sediment, right? So this really only works in peaceful coastal areas, or on very calm days, maybe you could do it. But you can't do it, even the days we were out there, no way. So once your waves are more than 20, 30 centimeters, you don't have a chance to do it. Which is why we start doing other methods. Okay, but
Cualquier parte de la costa atlántica con las olas que tenés, meter eso es como casi imposible.
so we can do this using the very simple steel drum methods. Over time, people tried to develop automated seepage meters that would actually, you could just put it out there, because this also requires a lot of manpower, right? The manual method, a lot of personnel that have to go out there and measure these things all the time and put them on and put them off. And often the water can be a bit deeper depending on the tide. I've worked in areas with 4-meter tidal levels, so at low tide it's okay, but at high tide you can't easily get to the seepage meters. So it's a good method for simple coastlines. It's a good method for simple coastlines. So we tried to develop automated seepage meters that are using things like propellers to measure flow inside, or electromagnetic currents to measure flow inside the actual seepage meter. One of the earliest ones was this, what was called the NAS 3X seepage meter, which was created by Woods Hole Oceanographic Institution. And it actually uses dye dilution technology. So it has a sensor that measures color in it, and by how fast the color dilutes, so how it reduces over time, it can then recalculate how much water is flowing through the seepage meter. It was a really cool idea because it was also, at the same time, a nutrient analyzer. So you can analyze nutrients and the flow at the same time. This thing cost about 20,000 euro for one seepage meter, and I had a grant to use it, and it broke every time. It was like the RAD 7, but everybody breaks these, not just me. It was a very difficult piece of equipment to use. So it kind of died out. And the truth is that the automated seepage meters, they just were too complicated for too little of a surface. So people stopped using them as much. This was the setup for that NAS 3X system. So we started to move on to other ideas. And this was originally an idea by Thomas Stieglitz from Australia to measure the bulk ground conductivity in the sediment, or basically the opposite of the electrical resistivity of the sediment. So when you have a low bulk ground conductivity or a high resistivity, you're more likely to have what kind of water? Fresh or salty? Fresh water. So he had a system where he had 2 poles with anodes on them, and he would put them in the ground, and he would measure the conductivity between the poles. And so he was able to just kind of walk around the coastal area and look for where the fresh water was coming closest to the surface. And so together we did this in multiple different locations, and what we were able to find was that, sorry, that's the pole. What we were able to find is that generally, so I was measuring via the point seepage meters, and he was measuring with the poles, that where he had low bulk ground conductivity, I found relatively high discharge. So it worked well. What was nice about this idea is that you could then go first with the poles around and look for where the fresh water comes close to the surface, and then you could go out with the seepage meters and put them there. Right? So because it takes time, it's like trying to find a needle in a haystack. But this was a much easier way to determine, and that's why what Santiago was doing on the coastline there, looking for where the fresh water is a great start. And we took this to another level, where we actually were able to create an array that you could drag behind a boat. And so you could slowly ride around the coast looking for where the fresh water comes close to the surface. But these are very expensive things to do. Very difficult, very expensive. But when you do find it, then you can put in the seepage meters to try to determine how much water is flowing. So the bulk ground conductivity in and of itself doesn't give you a quantification of the groundwater, it just gives you the location. It's kind of like the radon method before radon method happened. Okay. So this brings us to a very large technological jump in measuring groundwater. With both the point measurements and the bulk ground conductivity measurements, we were very confined to small places over a long period of time. And when it comes to trying to understand just a little bit of a coast, a few hundred square meters, it was good. But if you wanted to understand how much groundwater was coming out along an entire coastline, or if you wanted to understand how much groundwater was coming out into an entire lake or lagoon or coastal embayment, it was impractical to do it that way. So a couple of scientists started thinking about why not use naturally occurring radioactive isotopes to trace groundwater flow. So in a lot of sediments, we have uranium and thorium. Uranium and thorium is mostly in a granitic sediment, or bedrock, I should say, in a granitic bedrock, but that granite wears down over time and eventually goes to the coast, and a lot of the uranium and thorium will then come to the coast with it and be buried there. And so we have two ways to look at this. One is via radium. And radium was kind of the first step of looking at naturally occurring isotopes in the coastal zone. So we have 4 isotopes of radium: 223, 224, 228, and 226 radium. They all have different half-lives. 223 and 224 are very short-lived isotopes. 3.6 days for 224, 11.4 days for 223. So that can measure short coastal processes that are occurring. We also have long-lived radium isotopes, so 228, which is 5.8 years, and 226 is 1,600 years. So this is good for large oceanographic studies. And if you remember from before, Billy Moore said with the 228 radium, we have 3 to 4 times the amount of fresh water coming via groundwater than rivers. So he uses the long-lived for that because he's out in the open ocean. But in the coast, we tend to use the short-lived radium isotopes to measure. And the nice thing about radium isotopes is you can go out with your boat and you can go along the coast and you can collect samples and then filter them and measure them. And the way it works is you collect fairly large samples. So 25 liters, 50 liters of water from your spot. And then you slowly filter them, less than 1 liter per minute, through these columns, which are impregnated with manganese oxide fibers. The manganese oxide takes the radium out of the water and it puts it onto the fiber. So the water that comes through here, is radium free. All the radium is in the fibers. Then all you have to do, instead of taking 50 liters of water back to your lab, all you have to do is take your fibers back to the lab. You take the fibers back to the lab, you dry them for about a day, and then you can count them in this system which is called a RADEC system. And that counts by alpha detection with the delayed coincidence counter. That's for the short-lived isotopes. You can then turn the fibers into powder, into pellets, and then you can put them into gamma spectrometers to measure the long-lived radium isotopes. So we can measure all 4 radium isotopes. And we did this. We did this a lot. And tomorrow I'm going to tell you, I don't think I have time today. I was planning on doing it tomorrow. Tomorrow I'm going to tell you how to take this and quantify into an SGD calculation, but today I'm just introducing it. And so we did this a lot. We did a lot of what we call radium mass balances. What is a mass balance? What's a mass balance?
It's a balance between the mass that's getting into the system and the mass that is leaving out.
Exactly. So,
In Jamaica, it's better.
yeah, although that's Jamaica and New York. It's Queens.
Only the name, not the place.
Well, I will talk about Jamaica in the Caribbean Sea tomorrow or in the next days, but this is Jamaica and New York. So the idea of a mass balance is what goes in must equal what goes out if this is in steady state. If what goes in is more than what goes out, then this should be going up. If what goes in is less than what's going out, then it should be going down. But the idea behind this is that we're in a steady state. And so if we know what's going in via water that's coming, let's say this is a bay or a lagoon, if we know that what's going in via the water that's entering the lagoon, water that's coming from rivers, water that's coming from any other potential surface source like runoff, if we know what's going in via diffusion through the sediments or percolation through marshes, and we know what's going out via water that's leaving through the inlets and decay, because radioisotopes decay over time, then we can figure out what our unknown is, which is groundwater. So I'll get into this much more in depth later or tomorrow. But we do these mass balances, and I will go through all of this, all of these different ones. Because it's similar for radon as well. Okay, so we did this a lot, and it's pretty fun work. You go out there, you collect your samples. This was in Jamaica Bay, New York. JFK Airport is basically right behind us here. And we're standing on a marsh there, and you always need to kind of use gravity to filter them. So you build them up. And while we were out there doing this work, a few minutes later, the New York Police Department gunship came out and literally launched this boat with guys with machine guns coming towards us. Luckily, they didn't shoot first and ask questions later, because the pilots of the planes were reporting somebody was building a missile silo on the marsh underneath the plane track. Anyways, so we did this work, and we got a lot we did this in many different places, and I'll explain the answers that we got from that later. But radium became a very popular way to quantify SGD. But through that time, people were starting to wonder, is radium really the best way to measure SGD? Because radium has this salt issue that it releases when it comes into contact with salt water. So we started to think maybe radium is not the right element, but potentially radon is. Because radon is a gas. It's not attached to the sediments in the sense of being released when it hits the salt water. It just always is releasing over time as a gas. So it's a better tracer. It's still in the uranium-thorium time series. So it's still coming from the rock. It's still elevated in groundwater compared to open water or seawater, so you can still measure it, but it has nothing to do with salt. So once again, we're in the uranium-thorium time series, and you can see that radon is actually a daughter of radium-226. So it's the same idea. It's still coming from the rock, but what makes radon unique is radon is not affected by salt. So it's a really good way where we can measure groundwater versus surface water. It's also inert, so we don't have to worry about these impacts or changes that are occurring in the water column. It has no chemical issue with the water itself, and it's really easy to measure, unless you have water on it and then it falls apart. And we measure it with this piece of equipment here, known as a RAD7. Now they've got a new one, it's called the RAD8, which can get water on it, apparently. This one struggles with that. And this is, and we could pass this around, maybe people should come up here and look at it at some point in the next day or two. But this is our radon detector. This is the radon detector. And basically, RAD stands for radon in air detector. Radon in air detector. So how, if it's radon in air, how come we're using it to measure water? So, difficult. What you do is you connect a pump of water to some sort of gas water exchanger. I'm not sure if I have that here, let's see. I'll go back. You measure, you pump water through some sort of gas water exchanger. And I'll show you this in the next days, what that gas water exchanger looks like. And the gas, the water just goes through the gas water exchanger, but the gas gets pulled into the radon detector. The radon gas gets pulled into the radon detector, and you measure continuously for 5 minutes in what's called sniff mode. And for those 5 minutes, it's measuring the alpha decay of radon into polonium-218. So it's actually measuring alpha particles. So once again, radon is a radioactive isotope. It decays, its half-life is 3.8 days, so it decays quite rapidly. And as it's decaying, it's releasing alpha particles. And those alpha particles hit a sensor inside the detector, and that's what it's capturing. And what it gives you an activity of radon. It's not concentration. People often confuse that. It's similar to concentration, but it's activity. Activity is how active it is. It's how often it's decaying. And that decaying, that activity, the units are becquerels, BQ. Per cubic meter. Becquerels per cubic meter. So it's an activity per cubic meter. And so it's measuring this activity. You pump the water up, the water goes through the gas water exchanger, the gas is pulled into the radon detector in what we call sniff mode. You let it measure for 5 minutes, and what it's measuring is the alpha decay of radon. This was actually developed not for coastal marine research. This was developed for your basement, or at least Americans' basements. We have a lot of granite in America, and we have a lot of houses built on granite. And so the radon actually goes into your basement, and if you don't ventilate your basement, radon can be very dangerous. It can cause cancer, and therefore we need to measure, if we have basements that are in granitic areas, we need to measure the radon. And that's why it's a radon and air detector. So normally, when you're measuring in your basement, you're not leaving it on for 5 minutes. You just leave it on because it's in the middle of the air for 24 hours. And it's just measuring for 24 hours. But in our water system, we can do it much quicker than that, especially when we're looking directly in water from wells. There's so much radon in the wells that you measure it very quickly. So what's good about this is you can easily take this system, theoretically, if you cover it now with saran wrap, you can easily take it onto a boat. Look at that handsome fella right there. Onto a boat, good captain. And you can pump the water through the system. Here's our gas water exchanger. I'll bring that in so you can see what it looks like. And then that goes into the radon detector. And with that, you can slowly ride around your coast and measure radon in situ. And think about this, compare this now to radium. Radium, you had to collect 50-liter samples of water. From one point, you had to collect this 50-liter sample of water, you had to filter it, go back to a lab, dry it, measure it. It was a lot of work. Now with this little guy, you can just go on a boat, have a really relaxed time, drink your mate, and go around and measure radon.
Taking samples every 5 minutes.
Every 5 minutes, but it integrates for 5 minutes. So the 5 minutes is the 5 minutes before. So you always have your GPS, you know where you are for the 5 minutes. It's like you track how far. So your 5 minutes measures the distance you travel over those 5 minutes. So if you want to know exactly where the groundwater is coming out, you have to basically sit for 5 minutes and then go somewhere else. But if you want a sense, so a good idea, then you can travel slowly. And you know that the last 5 minutes is what it measured. And I'll show you some of what that looks like probably tomorrow. Today I'm just introducing the subject. Yeah, so this is a few years ago. We've done this now a few times along the coast here, and it's interesting. We'll go through this as well tomorrow. So now we've had this evolution in how we measure SGD. We started with point measurements and bulk ground conductivity, and we've moved into radionuclides and radon, and it's created kind of an explosion in the amount of scientific research on this subject. I started doing SGD work right around 2002. And there was very little information out there back then. And now you can see it's really gone up. And one of the reasons it's gone up is because of how easy these things are theoretically to use. And so we're learning more and more about SGD over time. And this is obviously ending in 2019. It's gone up a lot since then. It continues to go up. And if you do a search for SGD, or submarine groundwater discharge, you get these kind of search terms that show up now, right? So you have submarine groundwater discharge is your main one, groundwater discharge. You look into it, subterranean estuary nutrients is a big deal. Obviously we're trying to quantify it, and seepage meters are kind of now off to the edge You can see radon is right in the middle. These are all of our search terms in a special type of way of looking at it. So we now know groundwater is everywhere. Billy Moore says that, groundwater discharge is everywhere. Billy Moore says that it's 3 to 4 times greater than river discharge. So why do we care about it? Why do we care? For many reasons. For many reasons. So this is a great image. I love this image. Found this recently. This is looking at all of the impacts of groundwater discharge, let's say inland to the coast. And it looks at estuaries, and plus means it has a positive impact. Whatever color that is a neutral impact. I guess it's yellow. And minus is a negative impact on the coastal zone. And the truth is, we're still learning a lot about this. We're still learning a lot about this. Okay, so one of the first places we started to look at this is in estuaries. Coastal, really near shore coastal areas. And we know that in estuaries, SGD has both positive and negative impacts. We know that SGD is delivering nutrients to the estuary ecosystem, which at low levels can be good, at high levels can be bad. It's a source of trace metals, which surprisingly in estuaries, a bit of trace metals can be a good thing, a bit, because some of them are natural, but if it goes too much, it can be bad. And it can also be a source of other pollution. Coral reefs, I'm going to talk about a lot in the last 2 classes, because I think this is an unknown situation with SGD. There are lots of people that say it could be positive for SGD, for coral reefs. It could promote growth, but there's a lot of others that say it could lead to coral bleaching. And when it gets to coral reefs, there might be even more complicated parts to this. And as we all know, coral reefs are extremely vulnerable at the moment, and therefore it's an important place to look at. Mangroves, similar issue to estuaries, and also incredibly important. We kind of separate estuaries and mangroves. Estuaries are more, in this sense, temperate areas, and mangroves are more tropical. Also coastal community, we see it could be a potable water source. And what's really interesting is this part here. Maybe it prevents saltwater intrusion, which if you have this SGD pushing out, it's harder for the saltwater to come in. Which is for this coast here, extremely important. Land subsidence, if you take too much groundwater out, you might have subsidence of land as well. There's some evidence that in the nearshore area it could lead to fish kills, and I'll go into that in a few minutes. And it can also promote primary productivity. So there's a lot of these. It's good, it's bad. We're not sure. We're trying to learn more about it. But it is important. Whether it's good or bad, it's important. So we want to learn more about it. Okay. So the first thing here is that SGD is a source of nutrients to the coastal zone. Nutrients are obviously vital to coastal ecosystems, and the abundance of those nutrients is kind of a fine line between being important and being too much. So we have to try to understand the role that groundwater plays on nutrients. And this is kind of the holy grail of SGD, is nutrients. This is why so many people wanted to start. After the idea of fresh water, drinking water, nutrients was the second big issue. So back in 1980, here, this famous article by Johannes talks about the ecological significance of submarine groundwater discharge, and he's mainly discussing nutrients. And what he says is in Austria, data suggests that submarine groundwater discharge delivers several times as much nitrate to coastal water as does river runoff. So this is really a boom moment in these studies. This is what drives SGD research for a long time, is this attempt to try to understand the role that groundwater has in nutrients. The role that groundwater has in nutrients. And those nutrients are nitrate, and what's the other one? The other main nutrient that we're worried about in the coastal area? Phosphate? Phosphorus? Phosphate? So, we're trying to understand how much SGD can bring in terms of nitrate, or nitrogen, and phosphate, or phosphorus, to the coastal area. So this is a big deal. In most coastal zones, what's limiting? Nitrate or phosphate? Nitrogen or phosphorus? Do you know what I mean by limiting? Limiting is the limiting nutrient determines whether growth is going to happen. If you add more of the limiting nutrient, you'll have biological productivity. In the coastal area, what's often limiting? Nitrogen or phosphorus? Who says phosphorus? Raise your hands.
But you have like all the nutrients that are existing on the continent, on the land. So like compared with open water, there the phosphorus is a limited near the coast. Nutrition.
So, if I heard you right, you said that the open water phosphorus is limiting, and near the coast nitrogen is limiting. Generally, that's correct. Generally, that's correct, because phosphorus, first of all, we need a lot more nitrogen than phosphorus for growth. Do you know what the ratio is, the general ratio of nitrogen to phosphorus? So there's this, what we call the Redfield ratio, and that's carbon to nitrogen to phosphorus, and it's 106 to 16 to 1. So we essentially need 16 amounts of nitrogen to phosphorus. That's our perfect ratio. And generally in the coastal area, it's more like 12 to 1. So if we add nitrogen, we get growth. Generally. Sometimes it's different. In the open sea, phosphorus is more limiting because phosphorus comes directly from the rocks. Sometimes bird shit as well, but a lot from the rocks. So in the coastal area, if we get nitrogen, and it can't just be nitrogen, right? Nitrogen is everywhere. We have more nitrogen in our air than we have oxygen. So it has to be the usable form of nitrogen, which is nitrate, which is NO3, or nitrite, which is NO2, or ammonium, which is NH4. These are the three usable forms of nitrogen for growth. So these are often limiting in the coastal area. Nitrate we get when we have oxygen available. What do we have, nitrate or ammonium? Nitrate, right? So here we get in oxic waters, and this is in anoxic waters. But all of these are usable for growth. They're all usable for growth. So we're really interested in how much, specifically nitrate, is coming in through groundwater, and in some cases, ammonia. Nitrate is really an intermediary. It doesn't exist too much naturally out there. It's usually kind of going in one direction or the other. So we're looking for nitrate. And we've been looking for it for a while. So that's 1980. Another paper came out in 2004. So 24 years later from the original paper. This is more or less the second paper that really talks about nutrients. So nutrient inputs to the coastal ocean through submarine groundwater discharge, and they start to look at really what's happening in the coastal area. So in where we have oxic groundwaters and we have oxic seawaters, then we get a lot of nitrate that comes in through groundwater and through seawater recirculation, and therefore our nitrogen to phosphorus ratio is much bigger than Redfield. So in this case, phosphorus would be limiting. When both are oxic and we get the nitrate coming out, then phosphorus is limiting. And then we need to get more phosphorus in the water. This is not a case that we see that often, but when we have oxic groundwaters and anoxic surface waters, or let's say low oxygen surface waters, we get to have a lot of biogeochemical processes that occur where we have nitrification, so ammonium that goes into, when it goes from the anoxic seawater towards the oxic groundwater, we get nitrification, so the ammonium goes to nitrate and then denitrifies to nitrogen gas and is released. We get some phosphorus formation in this case, so we get this ratio drops a bit. In case 3, which happens more often, we have anoxic groundwaters and oxic seawaters, and we get a lot of denitrification that occurs in the anoxic groundwaters, so the nitrate goes to nitrogen gas and is released. We get some nitrification which occurs in the subterranean estuary where we get the ammonium turning into nitrate. And we get this recirculation of nitrate here. And we get iron, phosphorus, and calcium phosphorus reactions in the subterranean estuary. And in anoxic conditions, we tend to get a lot of denitrification that occurs, so the nitrate is released as nitrogen gas. And we get a bunch of phosphate changing into calcium phosphorus formation in the subterranean estuary. So what they're showing is that the process with the subterranean estuary becomes quite complicated when we have these mixings of waters. So we know that nutrients are coming through groundwater, but it's getting very difficult to measure that. And we're still trying to find the answer. So this is a paper we published last May, not last May, 2 Mays ago, in Germany in the Western Baltic Sea, where we try to really link the nutrients to the discharge. And this is kind of the best image I could pull from that, but basically we had seepage meters along this bay called Eckernförde Bay, and we were also measuring salinity in the pore waters as well. And generally where we saw low salinity, we tend to see a bit higher, I'm confusing myself. Yeah, where we saw low salinity, we tended to see a bit lower, or a bit higher nitrogen in there. Confusing myself. And phosphate didn't have any real connections to it. But we did measure higher nitrogen where we had lower salinity in the sediments. And that's also where we had our highest SGD. And then going further with this, when we have a lot of nitrogen coming out, we tend to get a lot of harmful algal bloom events. We tend to get a lot of harmful algal bloom events. So this work by Natasha and her group shows that in this area of Alabama, which is famous for seasonal fish kills, so a lot of fish dying, that submarine groundwater discharge can be almost directly linked to the location of those fish kills. So here she shows the radon anomaly, where we have high radon along this coast. And this is also the most common area of jubilees. And jubilees, strange name, are the local name for fish kills. So here, when we have a lot of radon, and also higher resistivity, so more fresh water in the ground, we get the most common location of jubilees. So we know that this groundwater is coming out, and we know that the nutrients are coming out, and those nutrients in certain cases are too much, and they're leading to harmful algal blooms, which then translate to fish kills. So some negatives associated with it. Many years ago, my colleague here, Aaron, and his professor, Kirk Cochran, put together a study of trace metals in Jamaica Bay as associated with submarine groundwater discharge. And what they found was, it was a bit tenuous, but what they found was that at levels of higher radium, that we get more lead, higher usable lead ratios in the ground, in the bed. So it seems that groundwater is linked to release of lead in Jamaica Bay. The trace metal connection was very difficult, and so for 15 years there were very few articles that came out on trace metals in association with groundwater, but more recently, in the last few years, we're getting more articles coming out that are directly linking groundwater discharge to trace metals in urbanized bays. So here, for example, if you look at the zinc, arsenic, cadmium, chromium, lead, and the, I guess, total heavy metal flux in this bay, in almost all cases, SGD is bringing in more trace metals than the rivers. The rivers are in black, and SGD is this hollow. So SGD seems to be really important for trace metals, at least in this urbanized bay. So we know we're getting nutrients coming out. Those nutrients can lead to harmful algal blooms. They can lead to fish kills. We know we have trace metals coming out at too high levels, obviously. All of these things are toxic, right? All of these things are toxic. Arsenic is extremely toxic. Do you know what arsenic does to you? Cancer is one thing. And one other thing that's really bad that arsenic does. Biologists.
In tooth.
In the tooth, maybe I don't know, maybe about that. But one of the big things, arsenic blocks.
El hidroxencismo genera dientes marrones.
Arsenic blocks the electron transport chain. It stops ATP from forming in your cells, which means you have no energy anymore. You have no energy, you can't live. So if you really get arsenic poisoning, it's really bad for you, because it's essentially a receptor that blocks the electron transport chain from occurring. So instead of producing 32 ATP per molecule of glucose, you're only producing 4. And that's not enough for us to survive. So arsenic's really bad. And arsenic is often found in groundwater. So if it's coming out into the coast, it's a bad sign. Okay, so there are a couple coastal areas that have real direct connections with SGD, and a couple coastal ecosystems where this process is extremely important, and one of them is mangroves. In mangroves, we get a lot of dissolved inorganic carbon and dissolved organic carbon coming into the mangroves via SGD, and also going into the coastal zone. So this is releasing a lot of CO2 to the atmosphere. This is releasing a lot of CO2 to the atmosphere. So we have like a massive source of carbon dioxide from SGD in areas with mangroves. So instead of being the CO2 being taken up into the mangroves, it's being released into the SGD and going into the atmosphere. And this is extremely tidal related. So if you look at it, at this graph here, when the tide decreases, the SGD, or radon, SGD increases. So at low tides, the SGD basically releases the carbon dioxide to the atmosphere in mangrove systems. So at low tide, the SGD releases carbon dioxide into the atmosphere in mangrove systems. In coral reefs, I'm just going to briefly talk about this, introduce this subject. This is something I'm very interested in right now. SGD seems to have a major effect on coral reefs, but we don't exactly know what that is yet. It's a new topic to study, so if anyone's interested in this, this is something that will be important in the next few years. So, several years ago, I was in Jamaica, and funny enough, but the resorts were really concerned about the coral reefs in Jamaica because so much of the tourist dollars was based on a healthy coral reef. So they wanted to rebuild coral reefs by making coral nurseries. So they spent a lot of money to set up coral nurseries in Jamaica. And some of these coral nurseries were mysteriously dying. They weren't surviving. And they didn't know why. And so we, mainly my old professor, had the idea that maybe these coral reef nurseries are located near submarine springs. Because if they're located near submarine springs, and those submarine springs are bringing in a lot of nutrients, then you'll get algal growth over the nurseries. And the algal growth will then block the light that the corals need to grow. And so what we did was we took a helicopter flight over the north coast of Jamaica, and we looked at the thermal signal in the water. Why did we use the thermal signal?
Because groundwater is colder.
Because groundwater is colder. Why is groundwater colder? What's the temperature of groundwater based on? The mean annual temperature. The mean annual temperature. So even if Jamaica is in the Caribbean, it has daytime, it has nighttime, it has a mean annual temperature that's lower than the surface water temperature in most times in the year. Also, Jamaica has fairly high elevation, and a lot of that groundwater is probably in the form of precipitation at 1,000 meters or 1,500 meters, and so that's colder up there. And so then it's going into the either the limestone on one side of Jamaica or into the volcano on the other side of Jamaica and coming out as springs. And it's coming out at colder temperatures. So we flew over the north coast of Jamaica and we looked for the thermal signals. And where we found colder temperatures, we then went out on a small boat or a kayak, which I'll show you in a couple days, and we looked for radon signals. And the radon, where we have the lower temperatures, and the radon would spike right where we have the lower temperatures. And then, this was the most fun part, then we dove off the boat, and we went down and we searched for the actual springs. So we could really map them. And the interesting thing is, almost every place where the coral nurseries were dying were located close to springs. Almost without a doubt. And so, there's clearly some sort of connection between groundwater and at least coral nurseries. This was not healthy reefs. They were developed reefs. So that's a different story, which we'll talk about as well. But this was for the nurseries itself. So when it comes to trying to understand how to restore a coral nursery, maybe it's really important to understand where groundwater is coming out. And the thing is, often tropical islands, well, let's say non-atoll tropical islands have spring systems. It's less of this diffuse discharge that we have here on the coast. It's more of the springs. So more of that intense point discharge. So SGD may have a really important impact on coral reefs. People have been looking at this in Hawaii, in Tahiti, trying to understand using radon where SGD may be occurring, but no one has really looked at it directly in terms of coral nurseries other than us so far. But one thing that seems to be very clear with SGD is that a lot of carbon dioxide is coming out via SGD. And when we have carbon dioxide that's coming out into our coastline, what happens to the pH of the area? Well, it goes down.
Yeah, it's really nice.
So we get ocean acidification associated with SGD. And so this is a study from Wang et al. In 2018, looking at the aragonite concentration changes and showing basically that when we have SGD, high levels of SGD, we end up having high partial aragonite concentrations, which suggests lower pHs. And when we have low SGD, we tend to have these lower aragonite concentrations. So it seems like the SGD is affecting, even on a daily time scale, is affecting ocean acidification. And as we know, ocean acidification is a problem for coral reefs. So right now, I mean, most of the things that I talked about today were kind of negative impacts of SGD. But we will talk about some positive things as well in the next class or the next classes, seminars. But what we do know so far is that SGD seems to be happening in a lot of different coastlines. Sometimes as point discharge as springs, and other times as this diffuse discharge, and that's the more frequent way. There are many techniques we use to measure SGD, but I would say that the best way to do it is to mix both point measurements and integrated measurements where possible. So both actually going out with seepage meters and doing some integrated measurements where possible. And SGD likely plays many important roles in coastal processes. Okay, that was kind of an introduction today into this topic and why we're interested in SGD. Tomorrow, we're going to go into how to actually quantify it. So we'll go into the math behind quantifying SGD using radionuclides a little bit deeper. And then what we're going to do is a GIS analysis of how to do this work. But we're going to do something simple. We're going to use a digital elevation model to look for where SGD might occur. If anyone has or wants to work with me tomorrow, you can bring in your computer and do this GIS work together. So you can learn how to make these watershed models via GIS to pinpoint where SGD might be coming out. Who works with GIS? Couple people? If not, it'll be interesting to watch, to see how it works. The beautiful thing about GIS, and this is do you have a question? No, you work with it. Yeah. The beautiful thing about GIS is that GIS has become so much easier to use over the years. And now it's free, right? So back in the day, you needed to pay a lot of money for an ArcGIS license or be part of a university. Now, anyone can use QGIS for free, and QGIS is wonderful. And so tomorrow, well, if you want, bring in a computer. Do you have everyone's email addresses, by any chance?
They have it at the office.
Okay, if not, I'll just bring in a stick, and then we can put the data on your
Okay.
computer, so you can work with it.
It would be maybe.
Or maybe I can find a download, that's easier. But then we'll just do a little exercise together on GIS and see how you can find potential groundwater locations with one digital elevation model, which is pretty cool. All right, yeah, I think that's almost time already. Oh, it is. Any questions? Yeah.
I didn't understand why the discharge is higher when the tide is lower.
So when you have for those people watching online, the question is, why is discharge higher when the tide is lower? So if you just think of, we'll try to do this as simple as possible. Time to go, huh?
Se desconectó. ¿No? ¿Eh? Sí.
Es una presión dependiente. Baja el nivel del mar y no pendiente.
Okay, so when you have high tide, this is your water table. This is then the sea. When you have high tide, your DH is this little one here. When you have low tide, your DH is now the bigger one. So the DL is this from here to here is the DL. The DL doesn't change, but the DH gets bigger. So you have more flow.
Es como bajar el nivel de base de Submarine.
Soy de Kiel.
Pero básicamente la marea alta te empuja el agua para adentro y no te lo deja bajar.
Ah,
Y la
no,
forma
sí.
más clara que lo puedo explicar sin gradient y todo eso. El frente marino no te deja bajar el agua. Cuando va a bajar la marea, el gradiente se restaura
Con la ley que había dado él.
el descarga, la diferencia de la altura hidráulica, la altura del mar y la altura de la cúpula.
A comment on our question. When you have a submarine discharge, always below the sea level, no?
You're right.
In the case of the high tide, you have a higher pressure over the point. When you have a low tide, you have a lesser pressure.
Yeah.
In that case, you
Allow the waters easier to move out. Absolutely. So pressure has something to do with that.
pressure has to.
And we've also seen that in an area where we have a barrier island. And when the tide is higher on one side of the barrier island than the other, the pressure pushes the water through the barrier island. So you get an instantaneous discharge because it's a pressure. The pressure is instantaneous. So yes, it's also pressure related. You can also think overnight. I'll be here again tomorrow.
Yeah, it would be interesting to know a little bit about the waste water.
The wastewater.
Wastewater.
Do you mean sewage wastewater? So yeah, I mean, so we did that in Jamaica Bay, but that was from sewage treatment plants. We measured the radium in the sewage treatment plant. But you mean more if you have a house, it's a septic system, and it goes in and goes out?
In the need of contamination.
Yeah. Yeah, absolutely. So if you have any sort of wastewater that's getting into the groundwater, it's a massive source of nutrients and potentially other things as well.
John, in the case of the papers that you mentioned that they were lead or arsenic or whatever, they, I guess, I assume that they also studied the groundwater in the area. This groundwater has these elements, and then they found it on the discharge.
Yeah.
Okay.
Yeah. So they are also measuring the wells. And that's one of the important things that we'll talk about tomorrow is we also have to measure the wells on land to understand how much is coming from the groundwater.
Is it the same in the case of nutrients? They are in the groundwater in the land?
So yeah, so a lot of the nutrients are coming from the groundwater and the land, right? So you have, specifically in agricultural areas, If it rains, the nutrients get into the upper unconfined aquifer and then come right out.
They have an agricultural source.
Yeah, and a lot of times it's agricultural, that's a problem for the nutrients. So, I mean, there's also the sewage discharge, but sewage and agriculture are big ones for nutrients. And some of it's fertilizer, and some of it's just waste of animals. Okay, and we'll continue tomorrow with the quantification.
Thank you.
Thank you, John.